My name's Justin Lecurious. I'm here today to demonstrate EMAT technology. EMAT's an acronym for Electromagnetic Acoustic Transducer. It's a very low frequency form of ultrasound, and it uses several different modes of land waves, an SO frequency, an AO frequency, an S1 frequency, and an S2 frequency. It's generally used for pipe inspection, your dock lines, your transfer lines, your tank farm lines, lines that are not easily accessible. We've also used EMAT for tank bottom floor inspection that exceed your typical MFE inspection techniques. One of the main benefits for EMAT is you can inspect the full volume of the pipe itself without having access to the area. And the way EMAT works, it's a very low frequency and it uses a meander coil. The sound is generated in the coil itself by a magnet. The coil goes inside the cart itself, and a thin titanium plate is placed over the coil to protect the coil from the surface of the material being inspected. Since there's no liquid couplant, the surface of the material, the pipe, doesn't have to be cleaned, and doesn't have to be prepped. We've inspected pipes that were half submerged and half buried in grade with about that much access. And at the soil and at the earth bank, you can see scale, exfoliation, corrosion from the atmosphere, from rainwater. And instead of the client or customer having to dig out the pipe, we could access the top section, just 1/3 of the pipe is required, and do a full volumetric inspection of the pipe without disturbing the soil. These two signals, they separate your data. So if you're scanning a piping system and you get a signal response in your long path, that's a key indication that you have an area of degradation somewhere in this region. Vice versa with your short path. Your amplitude is based on the thickness of the material being inspected. This is an 8-inch pipe. I think the nominal wall is 0.322. Your time of flight is based on the time it takes for your transmit probe to send signal to your receiver. On this calibration piece, we have 3 notches. These flaws represent a holiday that you would find on a docking system or a piping system over a wharf line. This one represents a 50% area of wall loss. This one is a 75% area of wall loss and a 25% area of wall loss. So when I scan across these defects, you'll see a signal response in the short path. Your amplitude will change due to the change in the material thickness. Your time of flight will also change too. Another form of the software is the real-time collection mode. Your red line represents your amplitude. Your blue line represents the time of flight, the time it takes for this sound path to travel from your transmit to your receiver. This is what is saved and collected. As you scan your defect, your 50%, you'll get a drop in amplitude, but you also get a drop in your time of flight. As you scan over your 75% defect, you get a drop in amplitude as well, much larger than your 50%. We can save this data image and reopen it again in an algorithm mode. This algorithm takes your data from both your RF, raw data images, and your real-time collection images, and it takes it to scale. And you can see your defects, your 75% flaw and your 50% flaw. So we could take a baseline reading and then come down to the lowest peak. Type in your baseline here in your lowest reading, and the algorithm does the calculation for you. As you can see right here, the estimated wall loss is 50.99% volume loss.